1.5 more on slope. And it's not a whole lot more because we're only 2 pages from one front and back here and we're done. All right, some things about slope we need to know. Slope with parallel lines. If two non-vertical lines are parallel, they have the same slope. So my slopes are equal when I'm dealing with parallel. Parallel have same slope. Okay. When it gives these two rules 2 and 3, they're really not that special, but it's just saying if you have two distinct non-vertical lines. So if you have a y equals 7 and a y equals 5, distinct means they don't have the same number. Obviously, if you have two like that, those are going to be parallel. Or if you have two distinct vertical lines, those are your x equals 6 and your x equals -5, something like that. Again, distinct meaning they have different numbers. Both will have undefined slopes. Both are parallel. So I think we can easily look at those two and say, yeah, they have to be parallel. When anything slants other than horizontal and vertical, we need the exact same slope. And remember, sometimes you have to reduce to see that you have the same slope. Okay, for perpendicular lines, if two non-vertical lines are perpendicular, the product of their slope is -1. That's very true. What does it mean to have a product that's -1? It means you have two fractions. When you multiply them together, you get -1. Or if you think about it, for those perpendicular, we've said for probably all our life that we get opposite reciprocals. Okay, so the reciprocal part will give us the 1 because a reciprocal times its reciprocal is 1, and the negative comes from the opposite. Okay, and then if the product of the slope of two lines is -1, the lines are perpendicular. That's kind of the same thing as number 1. A horizontal line having a 0 slope, so you just have to think if you have a horizontal line having a 0 slope, something like y equals 3, then if you also have a vertical line having undefined slope, which by the way can be x equals 100, whatever it is, 1y equals a number, 1x equals a number, those will also be perpendicular. And you don't see those slopes that multiply to get the opposite reciprocals, okay? So make sure you just recognize that those two will also be perpendicular. Okay, so it says use the given conditions to write an equation for each line in point slope form and slope intercept form. Okay, so let's make sure we're clear what we're doing here. We need L is perpendicular to the line y equals -2x. Okay, so this is the line y equals -2x, and we are trying to write the equation for line L. That's our job, okay? So we need to look first, what is the slope for our perpendicular line? Well, right now I have y equals -2x. Its slope is -2. It's the in slope or point the slope intercept form, and its slope is -2. What's a perpendicular slope? Well, opposite will make it positive, and when we flip, it'll make it 1/2. This is the slope I now need to use for everything else. I don't go back on it. I don't look back on that -2 slope. This is what I'm going to use. I need a point on my L. Well, they gave me one point there, an x and a y. I'm going to use that point. So I'm going to start out in point slope form. Y minus my 2 equals my slope times x minus my x, which is -1. I can clean it up just slightly. Y minus 2 equals 1/2 times x plus 1. And there's my point slope form. If I want to change it into slope intercept form, I'm going to distribute my 1/2 x plus 1/2, add my 2. If I add 2 to that, I can make it 2.5 or 5/2. That's probably the best way to write that. And that right there is my slope intercept form. Okay. Okay, so that used the graph, making sure that we knew what we were working through there. For number 2 here, I have my line is passing through the point -2, -7. I hope if I change my color. And it's parallel to the line whose equation is y equals -5x plus 4. All I need from this equation is my slope, which is -5, and my parallel slope is the same, so it's also -5. That's what I'm going to use for the rest of my work. So I'm starting with point slope form. Y minus my -7 equals my slope, which is -5, times x minus my -2. And I'm just going to clean it up to make it in point slope form. My minus negatives become plus. I get y plus 7 equals -5, parentheses x plus 2. There is my point slope form. I'm going to distribute and join like terms to get my slope intercept. I get y plus 7 equals -5x minus 10. Subtract 7 to the other side, y equals negative 5x minus 17, and there's my slope-intercept form. All right, next one. Passing through the point 5, negative 9, and perpendicular to the line, whose equation is x plus 7y minus 12 equals 0. I see that what I have here is what they call that general form. I would really like to change it into slope-intercept so I can see what my slope actually is. So I'm going to solve for y. Move that 12 to the right by adding it. Subtract x to the other side. Divide by 7. Now be careful when you divide by 7. This is actually like a negative 1 divided by my 7 and 12 divided by 7. To be honest, all I care about is this right here. I want this slope of negative 1/7. That's what I want. And because I'm going to be perpendicular to it, I need to find my perpendicular slope. So I'm going to flip that and go opposite. My perpendicular slope is 7. This is what I want to use. I needed to do this work to find the other slope. Going into point slope form, because I have an x and a y minus my negative 9 equals my slope of 7 times x minus 5. Cleaning up my y's, I get y plus 9 equals 7 parentheses x minus 5. Make sure you leave point slope form in a point slope form. Don't do too much simplification when you choose your point slope form. Now to change it into slope intercept form, I'm ready to distribute my 7. And now I'm going to subtract 9 to the other side. 7x minus 44. And there's my slope intercept form. Okay? So writing equations of parallel and perpendicular lines, be careful that you choose the slope you need for all your work first, and then you can ignore the extra information that came from the other pieces. Okay? All right, let's flip this page over, and let's do a little bit of, we can call it story problem work, right? We've got to love story problems. Okay, so a couple things here when you see this. So this is a typical story problem. You could see it on the PSAT, the SAT, right? Where it says find the average rate of change of a function, okay? That's some scary words. We're like, oh, what's the formula? What are we doing? Average rate of change is a fancy word for slope. That's all it is, okay? So when we're finding that, so if we look at this big box, what is this? Notice it says x1 and the function of x1 and x2 and the function of x2. It just means x and the y that goes with it. X and the y that goes with it. That's really all it means, okay? So when you see this big box here that says delta y over delta x, okay? Well, what's delta mean, right? It's a Greek letter, and it means change, the change in y over the change in x. That's all it means, okay? So there's nothing different here than any slope that we've already done. Again, it looks fancy on the top, the function of f of x of 2 minus the function of y x of 1. That means y2 minus y1. That's what those f of x of 2 gets you, is a y. And then over x2 minus x1, it's still just slope. So what you need to make sure you do is find what are my x's and y's that go together. So you'll notice here in the next equation that we have, or the next problem, that we have a function, f of x equals x squared minus 2x, and they give us an x. My x1 is 3. So if my x1 is 3, I'm going to plug in 3 into my equation or my function, and I'm going to find the y that goes with it, or the f of 3. 3 squared, well, I guess I could actually plug in 3 everywhere I see an x, right? 3 squared is 9, minus 6 is 3. So f of 3 is 3, okay? So x1 is 3 when it's y1, for lack of better thing to say here, is 3 as well. Okay, let's go for the x2, which is 6. So I find f of 6, meaning I plug in 6 everywhere I see an x. 6 squared is 36. 2 times 6 is 12. 36 minus 12, f of 6 is 24. So my y2 here is 24. Okay? So when I think about change in y over change of x, right? I mean, that's what, they have this great big thing, delta y over delta x. Okay? We just found our y's, right? We're going to do 24 minus 3 over 6 minus 3. 24 minus 3 is 21. 6 minus 3 is 3. We divide that, we get 7. The average rate of change there is just 7. It's the same thing as our slope, okay? So don't get scared there. If you want to say this, look at this. This right here was my f of, actually that was this one, f of x of 1, right? And this one down here, that was my f of x of 2. Okay, so I just plugged into this as well. It's just kind of how you think of these, okay? So don't get scared by all the notation because it's as simple as you're using slope. All right, average velocity of an object, okay? Yep, it sounds like we're doing a little physics here, right? And in some ways, we kind of are, okay? You use math in physics for a reason. Physics needs math so it can do the work it needs to do. Okay, suppose that a function expresses an object's position s of t in terms of time t. The average velocity is the change in s over the change of t. Is this any different from above? No, it's just now we're talking about the position versus time. Earlier we were talking about the function versus the x, okay? So it's all a matter of just wording it differently. The process and the thought behind it is all the same. Okay, so once again, if I have this function of s of t is 12t squared, if I know my time is 3, I'm going to plug in my time of 3. So s of 3 equals 12 times 3 squared. 3 squared is 9 times 12 is 108. Okay, so my 108 goes with my 3. T sub 2 is 4, so I'm going to plug in s of 4, and I'm going to get 12 times 4 squared. So 4 squared is 16. 16 times 12 gives me 192. Okay, so when I'm trying to find the ball's average velocity, that's the same thing as slope, right? So when I'm doing this, change in y over change of x. So I'm going to do s of t of 2, right? Minus s of t of 1. It looks so fancy and big and important, but stop and say s of t of 2. Well, here is my t of 2, right? And that's what I got once I plugged it in. 192. Can't write. Minus my s of t of 1. Well, that was the 108 I found. Over my change in time. Well, my change of time is 4 minus my 3. 192 minus 108 is 84. And 4 minus 3 is 1. The important thing is, because we're talking average velocity, my top number is 84 feet. My bottom number is in seconds. So make sure you get that label on there, 84 feet per second. Okay? Now, just kind of a quick visual so you can see this. Let's say, because especially this 12t squared, you're actually thinking about some kind of parabola, right? If I take this point here and I take this point here and I say I'm finding the slope, how close is that to the actual slope of that line? It's really not that close, okay? There's a pretty big gap. So we get this 84 feet per second, but really, is that an accurate slope, okay? It is for if we span the time over that much. But a lot of times when we take that slope, we actually want to narrow that span so it's much closer to the actual curve that we see in the picture. Okay, so on this second one, you'll notice I want to start again with T1 of 3. Okay, so I'm going to start here, T1 of 3 again, but this time I'm only going to go 3.01 seconds for my next one. I'm like right beside it. So I'm finding this, notice my slope is completely different now because I'm so close to my first point. So once again, my T of 1 is 3. We already did the math for this, but I'll kind of write it down again. S of 3 equals 12 times 3 squared. So we get this 108 a second time, right? If you want to, you can write it as an ordered pair. 3 goes with 108, okay? So now my T of 2 is 3.01, okay? I'm going to suggest get that calculator out. We're going to leave our numbers in our calculator, and we're going to leave kind of a long decimal because it will actually help us with a better, more accurate answer here. Okay, so S of 3.01. We have 12 times 3.01 squared. Okay, so go ahead on your calculator, 3.01 squared. Okay, leave that decimal in there, hit times 12. And I get about 108.7212. All right, I'm going to leave it. There's my ordered pair, 3.01, 108.7212. If we try to round too early, we could actually change quite a bit of this answer. So let's try to leave that decimal out. We have no need to not do it, right? We have the calculator, we have the use, so let's go for it, okay? Oh yeah, you don't. Well, we'll talk about chapter 2 chapter 1 when we can. Maybe we'll have a calculator, maybe not. Maybe if we do that on a problem like this, I just won't put a problem like this on there, okay? I'll keep that in mind. All right, change in S over my change in T, okay? So I get 108.7212 minus my 108, and I get 3.01 minus my 3. Okay, so obviously I subtract the top, and I get 0.7212 left over. Across the bottom, I get 0.01. The nice thing is it's 1, but I have these decimal places, so I roll 2 places to the right, 2 places to the right. I get 72.12, and once again, I want a label on there, feet per second. Okay? Now, is that different than this 84 feet per second? Definitely. Now, granted, we're not as far away anymore, so that slope was greater before. But you see this faster, or the more we stay together here, or the closer the 2 points are, that slope gets more adjusted to the actual curve, and it doesn't skip over those points. Okay? All right, that's what we have today. Not a lot, okay? But working off of our parallel and perpendicular slopes, and then thinking about turning that into story problem form. The process is you still have slopes. The difference is we call it average rate of change, average velocity, something to that effect. You need your x, you need your y's, and you find your slope, okay? So practice, page 200, 1 through 31 on, I don't know, do what Slater asks you to do. Just make sure you understand it. Good luck.